In the first lesson to this section of our STEM instructional program, we discussed the basic concepts of aircraft motion and how an aircraft is able to move in 3 dimensions. In this second lesson, we will explore the mechanisms that aircraft use to move in these 3 dimensions. We will discuss the basic flight surfaces that cause an aircraft to change direction and how those surfaces are controlled by the aircraft pilot. As was introduced in Lesson 1, an aircraft moves in 3 dimensions that we modeled using a 3-dimensional graph with an X, Y, and Z axis. In particular, we looked at an aircraft rotating around one or more of these axes. Early aircraft had flight controls that addressed each axis of rotation that could be used separately or with other controls to make the aircraft rotate in more than one plane at a time. In order to cause a change in the direction of motion of an aircraft, an unbalanced force must be generated. By Newton's second law of motion, if we generate an unbalanced force, the object will accelerate in the direction of that force. To get this unbalanced force and the resulting change in motion, we must develop a structure that will change the flow of air around the aircraft. This is most commonly done by making the back end of flight surfaces movable. If that moving surface is kept in a neutral position, there is no disruption to the flow of air around the flight surface. If the movable surface changes position, an unbalanced force is generated. In the example that we have here, by causing the back end of the surface to deflect or rotate downward, we generate a force that is perpendicular to the surface that is moved. We refer to this force as the normal force. This normal force can be split up or resolved into 2 parts or components. The first component is a force that acts in the same direction as the flow of wind. We refer to this force as the drag force, which would act to slow the aircraft down. The other component acts perpendicular or at right angles to the motion of the aircraft. We call this force the perpendicular force. That is the force that causes the aircraft to change directions. In this case, the perpendicular force acts in an upward direction, causing the flight surface to rotate upward. If the control surface is rotated in the opposite direction, the normal force and perpendicular force are also changed. The drag force still acts to slow the aircraft down, but the perpendicular force now acts in a downward direction, which would cause the flight surface to also rotate downward. The first rotation that we will examine in this lesson is rotation around the Y or vertical axis. As we indicated in Lesson 1 to this section, rotation around the y-axis is referred to as yaw. If we cause an aircraft to rotate around the vertical axis, it would cause the aircraft to turn to the left or to the right in much the same way as a car turns to the left or right. Yaw on most aircraft is controlled by a device called a rudder, which is located on the tail or vertical stabilizer of the aircraft. In many early aircraft, the rudder was the tail of the aircraft. In most contemporary aircraft, the movable rudder is located at the rear of a fixed vertical stabilizer. On many aircraft, a smaller movable control surface called a trim tab is also present. We will discuss the function of this control surface in the next lesson. The movement of the rudder is controlled by foot pedals located in the cockpit, commonly referred to as rudder pedals. The pedals in an aircraft have a completely different function than those in a car. The rudder pedals do the same thing in an airplane that the steering wheel in a car does. By moving the rudder pedals, we can change the heading of the aircraft or keep going in a constant direction. If the rudder pedals are kept side by side, the rudder stays at a neutral position and does not alter the flow of air around the tail of the aircraft, and the aircraft stays at a constant heading or direction. By pushing the left rudder pedal, the rudder is rotated in a clockwise direction. The normal, drag, and perpendicular forces are applied, with a perpendicular force pushing the tail in a counterclockwise direction, which causes the aircraft to turn to the left. By pushing the right rudder pedal, the rudder is rotated in a counterclockwise direction. The normal, drag, and perpendicular forces are applied, with a perpendicular force now pushing the tail in a clockwise direction, which causes the aircraft to turn to the right. By once again bringing both rudder pedals back to a side-by-side position, the normal and perpendicular forces are stopped while the drag force is minimized. The aircraft stops changing direction and remains on its new heading. Motion around the x-axis, or the axis that runs through the wings of the aircraft, is referred to as pitch. Again, as introduced in Lesson 1 to this section, pitch would cause the aircraft to rotate upward or to rotate downward. Pitch is controlled on most aircraft by movable fins located on the tail or horizontal stabilizer. These movable fins are called elevators. While there are two elevators on the tail of most aircraft, they work in synchronization with each other. The movable elevators are typically located at the rear of fixed horizontal stabilizers. Some aircraft also have trim tabs to support elevator function that are also located within the elevator at the rear of the horizontal stabilizer. In some high-speed, high-maneuverability aircraft, there is no fixed horizontal tail, and control surfaces are a single movable component called a stabilator or moving tail. We will discuss these and other flight surfaces in the lesson on advanced controls. The elevators are controlled in the cockpit by one of two types of controls, depending upon the type of aircraft. The cockpits of many aircraft contain control yokes that look similar to steering wheels in cars. Aircraft that have a higher degree of technology, and most fighter aircraft, have a control column that is similar to a joystick that you would find with most computer games. We will look at pitch control using the joystick first and examine how the control moves the elevators and changes the direction of the aircraft. With the joystick in the neutral position, the elevators remain in the center position, there are no normal or perpendicular forces, and the drag force is minimized. The aircraft maintains a constant direction. By rotating the control column forward, the elevators are rotated in a downward direction. The normal, drag, and perpendicular forces are applied, with a perpendicular force pushing the tail upward. This upward push on the tail of the aircraft causes the nose of the aircraft to rotate downward, and the aircraft descends. By rotating the control column backward, the elevators are rotated in an upward direction. The normal, drag, and perpendicular forces are applied, with the perpendicular force now pushing the tail downward. This downward push on the tail of the aircraft causes the nose of the aircraft to rotate upward, and the aircraft climbs. By returning the control column to the neutral position, the elevators once again return to the center position. The normal and perpendicular forces are eliminated, while the drag force is minimized. The aircraft would stop changing direction and continue on its current pathway, which could be a climb, descent, or level flight. Pitch control using the yoke is very similar to that of the joystick. With a control yoke at the neutral position, the elevators remain in the center position, there is no normal or perpendicular forces, and the drag force is minimized. The aircraft maintains a constant direction. By pushing the control yoke forward, the elevators are rotated in a downward direction. The normal, drag, and perpendicular forces are applied, with a perpendicular force pushing the tail upward. This upward push on the tail of the aircraft causes the nose of the aircraft to rotate downward, and the aircraft descends. By pulling the control yoke backwards, the elevators are rotated in an upward direction. The normal, drag, and perpendicular forces are applied, with the perpendicular force pushing the tail downward. This downward push on the tail of the aircraft causes the nose of the aircraft to rotate upward, and the aircraft climbs. By returning the control yoke to the neutral position, the elevators once again return to the center position. The normal and perpendicular forces are eliminated, while the drag force is minimized. The aircraft would stop changing direction and continue on its current pathway, which could be a climb, descent, or level flight. Motion around the z-axis, or the axis that runs from the nose to the tail of the aircraft, is referred to as roll. As introduced in Lesson 1 to this section, roll would cause the aircraft to tip either to the right or to the left. Roll is controlled on most aircraft by movable fins located on the rear edge of each of the wings. These movable fins are called ailerons. Unlike the elevators that work in synchronization with each other, ailerons work in opposition to each other. In other words, if one aileron moves upward, the other moves downward. The movable ailerons are typically located at an outboard position or near the wingtips. In some larger aircraft, such as commercial airliners, more than one aileron may be located on each wing. In other aircraft, ailerons may also be used as flaps for takeoff and landing. In these cases, these surfaces are called flaperons. On tailless aircraft, such as the B-2 bomber, ailerons may also serve as elevators and rudders, often referred to as elevons. We will discuss these and other flight surfaces in the lesson on advanced controls. Ailerons, like elevators, are controlled in the cockpit by one of two types of controls, depending on the type of aircraft. The cockpits of most civilian aircraft, commercial airliners, and heavy-lift military aircraft are controlled by a control yoke. High-tech aircraft and those requiring a high degree of mobility could be controlled by a control column. We will look at roll control using the control column first and examine how the control moves the ailerons and changes the direction of the aircraft. With the control column in the neutral position, the ailerons remain in the center position, there are no normal or perpendicular forces, and the drag force is minimized. The aircraft maintains a constant attitude. By rotating the control column to the right, the aileron on the right side of the aircraft rotates upward, and the aileron on the left side of the aircraft moves downward. The normal and perpendicular forces are applied differently on each wing. The perpendicular force on the right wing pushes the wing downward, while the perpendicular force on the left wing pushes upward. The combination of these two forces causes the aircraft to tip to the right. As long as the stick is kept in that position, the aircraft will continue to rotate in that direction. By rotating the control column to the left, the aileron on the right side moves downward, and that on the left side will move upward. The normal and perpendicular forces are applied, with the perpendicular force on the right pushing upward, and the perpendicular force on the left side pushing downward. This combination causes the aircraft to tip or rotate to the left, and to continue to rotate as long as the control column is held in that position. By returning the control column to the neutral position, the ailerons once again return to the center position. The normal and perpendicular forces are eliminated, while the drag force is minimized. The aircraft would stop its roll motion and continue on a straight pathway. This would not, however, return the aircraft to a level attitude unless it was either currently in level flight or rolled back to level flight. Roll control using the yoke is very similar to that of the joystick. With a control yoke in the neutral position, the elevators remain in the center position, there are no normal or perpendicular forces, and the drag force is minimized. The aircraft maintains a constant attitude. By turning the control yoke to the right aileron moves upward and the left aileron moves downward. The normal and perpendicular forces are applied, with the perpendicular force pushing the right wing downward and the left wing upward, rolling the aircraft to the right. By turning the control yoke to the right aileron moves downward and the left aileron moves upward. The normal and perpendicular forces are applied, with the perpendicular force pushing the right wing upward and the left wing downward, rolling the aircraft to the left. By returning the control yoke to the neutral position, the ailerons once again returned to their center position. The normal and perpendicular forces are eliminated while the drag force is minimized. The aircraft would stop its roll at whatever attitude it is currently in. Basic aircraft controls allow the aircraft to rotate around the y-axis or perform a yaw maneuver using a rudder located on the vertical tail, to rotate around the x-axis or pitch using elevators located on the horizontal tail, and to rotate around the z-axis or roll using ailerons located on the wings of the aircraft. There are a number of additional control surfaces that will be found on modern aircraft. Some of these controls will be discussed in a future lesson.